So we go to all this trouble. We have approximate models where we can maybe understand the general behavior for specific geometries, whether it's a pipe or a duct or odd shapes. It's often the case that you want to develop a correlation based on experimental data or based on some maybe self-similar solution or something that's maybe too complex to solve explicitly every time. So let's talk about internal flow correlations and what they give you, what they're telling you, and how to access them. So the first thing is let's get some definitions down. Correlations for internal flow are often expressed for shear stress using the Darcy friction factors. So this is Darcy. Darcy, sometimes called Moody friction factor. Okay, so that definition usually is just called F is equal to minus dP dx times 2 dH over rho um squared. So it's the pressure gradient times the hydraulic diameter divided by the momentum of the fluid. So what is this one giving you? I guess this is a local estimate of the friction factor. Right? F here is a local estimate because dP dx is going to be a local value. So this is this one is local. If you want the average friction factor, you can achieve that by saying F bar is equal to just P at x equals 0 minus P at x equals L divided by L. So that's our rough approximation of dP dx over that interval 0 to L times 2 dH over rho um squared. So this is average. Okay, so some similarities with the coefficient of friction. It's always with reference to the momentum of the fluid, but here we're looking at um squared, right, as opposed to u infinity squared. So that's the momentum of the flow in the constrained space, and then you're looking at dP dx as something that's present there as well. Okay, so that's on the momentum side. For the heat transfer side, I guess I've already written these, but I'll just rewrite them so you have them in one place. So we have Nusselt dH is equal to h dH over k, right? This is local. And then we have Nusselt bar dH is equal to h bar dH over k, and this is average. Right, so the obvious question is, like, how do we get these h bar values or f values? So you can do that either with a lookup table. You can have you can use e's to do that. So we can look at e's. And again, the thing that's important for this, before I get ahead of myself, the thing that's important for this is when you're going through the problem, you need to decide which of these things you're looking for. Okay, do I want to maybe compute the local and then integrate that myself? Or am I doing something where I really only care about estimating the parameter over the entire length, in which case I can just use the average. So you really need to go into it knowing which thing you're looking for, make that decision, and then look for the right correlation. So let's look at ease for a second. And ease, oh, by the way, a bit of an aside. This problem is an internal flow problem. I don't have time to go through it in detail, but it's in the lecture folder if you want to go through it. So for the homework, it might be helpful to see how this particular example goes through internal flow. Okay, so in ease, the way you would get to correlations would be, first you click on this heat transfer and fluid flow. In the first drop-down, you have to select convection. And then you're going to get a bunch of options. So this drop-down here lets you see maybe internal flow dimensional, internal flow non-dimensional, internal flow dimensional local, non-dimensional local, external flow, and so on. So you would need to go into this saying, all right, I know I want to get the local value. So you'd come down to here. You could do your dimensional or non-dimensional local. Once you pick that, local, then you can flip through here and see all the different geometries that are available. So there's quite a few, I guess. There's a handful. The difference between dimensional and non-dimensional is just that you're in dimensional, you are putting in dimensional parameters like m dots, x, those types of things. For non-dimensional, you're just putting in Reynolds number, Prandtl number, and getting back the values. So it's good to know how to use both. Let's see if there's anything else. Yeah, so if you do the local one, you are just getting the local value, obviously. If you're doing the not local one, ease is automatically determining the importance of the entrance effect for you. So it's doing that full integral from 0 up to your position. Okay. All right. So those are kind of how you access the correlations. The stuff that's going to come out of that would be like, should have maybe showed you, but stuff that's going to come out of that would be the Nusselt number. If it's a non-dimensional correlation, if it's a dimensional, you're going to get H back. And maybe a couple different things. So let's move on there. Okay, so looking at the momentum part of it, this is essentially, I guess let me flip over to the white version of this. You can see it. So this is a plot. This is essentially a correlation, right? But it's plotted out. You've probably seen this before. This is in every fluids textbook. So this is giving you the fully developed friction factor for internal flow in a duct as a function of Reynolds number. So maybe one thing that you haven't thought about before is, we now have this understanding of the laminar versus turbulent region and what's going on there. In laminar flow, you have this increasing momentum with Reynolds number. So you're going to see this kind of linear decrease on a log plot. But then once you get to turbulent flow, you have this kind of big transition. So up here, the stuff that matters is not roughness. Like you don't see anything to do with roughness. Over here, you just see stuff to do with like the shape of the duct. If it's a square, if it's a circle, whatever, parallel plates. So in the laminar region, the things that are important are geometry. And why is that? Right? Because the geometry affects how the boundary layers grow, like how they come together. Where in turbulent flow does not care beyond a few widths beyond the viscous sublayer what's going on, right? It doesn't care if you have a circular duct or square duct or whatever. It just needs to know what's the difference between my wall and just a few lengths beyond the viscous sublayer. So things that are important to the turbulent flow are things right near the surface. And what's right near the surface? Well, roughness is right near the surface. So here, geometry. Here, no geometry, doesn't care. Roughness is what's important. Okay? So maybe just kind of a new way of looking at that if you've seen it before. One other minor point to make here, let me zoom in so you can actually see it. So if we're doing F versus F bar, the function, so this is a fancy F for function, so that's just saying my function for local friction factor is going to take my Reynolds number in terms of a DH, right? It's going to take my local position, X over DH. It's going to take maybe surface roughness if it's turbulent, and duct shape if it's laminar. So those are the things that it could be a function of. If you go to F bar, then you no longer care about X, you just care about the total length. So there, everything's kind of the same except for L over DH as opposed to X over DH. So again, these are like minor details. As I'm talking about it, seems obvious, but when you do it, just make sure you be careful with that. Okay. Let's see what else we have. A few more minutes to talk through. So I showed you the lookup for the momentum problem. This is an equivalent lookup for the thermal problem. Again, here we have like Nusselt number local, Nusselt number average, and this plot, I can zoom in a bit more so we can see it. So this plot again is looking at laminar versus turbulent. So the same things apply for laminar or for momentum and thermal. here you have in the laminar region, you have things that are a function of just the shape of the duct or the shape of the opening. And one of the maybe interesting things here is if you have laminar flow, right, this is fully developed laminar flow, things aren't changing, right? So you can just memorize that if you have a constant heat flux, it is 4.36, right? That's your Nusselt number. If you have a constant temperature, it's 3 point, okay, memorize this, 3 point something. It's 3.6 or something like that, right? You can basically commit those things to memory and know if I have laminar flow, that's what my heat transfer performance is going to be in the fully developed region. Now, once we get to turbulence, things kind of change. And now it's a function of both surface roughness and the Prandtl number, the molecular Prandtl number. So the roughness parts may be obvious. Why the molecular Prandtl number if we're in turbulent flow? Right? That's maybe not so obvious. So we know that the turbulent Prandtl number dominates the heat transfer. But actually, if we look at the temperature gradient in the viscous sublayer, what is that temperature gradient limited by? It's the molecular properties in the viscous sublayer where there's no eddies. So Prandtl number is important to account for when you're looking at turbulent flow. Okay, questions on this? Okay. Let's see. Okay, so finally we can get to, in the last couple of minutes here, we can get to our formal analysis. We'll try to get maybe through just setting up the balance here. So let's say we have an internal flow that's occurring. Let's get back here. Come on. Okay, so let's draw our control volume here. So let's say I'm gonna take a control volume that spans the whole entire height. So we have to look at on an energy basis what's going in, what's going out, and then develop an equation for that. So going in from this side, we're going to have on an energy basis we have mass flow coming in, m dot times enthalpy I at position x. Right, this is dx wide. And then leaving, we have m dot I at x plus dx. If it's a thermal problem, you're going to have some interaction with the containing duct. So let's say that that's given to us in terms of a heat flux. So let's say going in here, we have q dot double prime s. And then that's going to be multiplied by the perimeter and dx. That's our total energy coming in. So let's assume that this is a steady state problem, so there's no du dt. Let's also assume that there's no energy generation, so just keep it simple. And then we can go through and develop the equations for this. So let's see, that's the control volume. So let's write this out. It is q dot double prime s times perimeter times dx plus m dot I at x is equal to m dot I x plus dx. So kind of skipping that intermediate step, we would end up with q dot double prime s times perimeter. dx's are going to cancel. We end up with m dot times di dx. We're going to assume I is equal to c times t for incompressible. And then we end up with q dot double prime s perimeter is equal to m dot times c dt dx. Right, and this is Tm, importantly. So that's our energy balance. Again, that's going to look familiar. This can be easily solved if q dot s is a constant. Maybe one thing to point out, so this parameter here, this is the heated parameter. That's any part of the parameter where q dot double prime is present. That's not the like hydraulic parameter. But yeah, so that's the energy balance. We could equivalently write this if we know that the heat transfer coefficient is, say, constant. We could also write this as, say, perimeter times H times Ts minus Tm is equal to m dot c dt dx, m dot tm. That's another way of writing it. It's just it depends on like what's given to us. So this would let us maybe solve for an unknown surface temperature or an unknown mean temperature, where this would let us solve for an unknown surface flux or vice versa.